Welcome to Study Loop.
A, the reason all neutral Rydberg atoms with the same N principal quantum number have essentially the same ionization energy independent of the total number of electrons is because Rydberg atoms have electrons in the outermost shell that exists in an excited state with a very large principal quantum number, which is N. Okay, so because of this very large value of N, the Z effective is equal to 1. Therefore, atoms have the same ionization energy irrespective of the number of electrons. This ionization energy is what I wrote out here, E, 13.6 electron volts divided by the principal quantum number N squared. So for part B, it wants us to calculate the energy, ionization energy. So ZE here is equal to 1, as we mentioned, when N is equal to 350. So here's our equation. We plug ZE equals into 1, N is equal to 350, and then you have 13.6 electron volts here. And we only actually care about the value, so we can ignore the sign. So plugging in those values, we find that E sub N is equal to 1.11 times minus 4 electron volts. So not too, it makes sense because the electron's very far away, so it wouldn't take much to excite it. Now the radius here, to calculate the radius, is N squared times A, where A is Bohr's radius, so 5.29 times 10 to the minus 11 meters. So this value for R equal to 6.48 times 10 to the minus 6 meters. We can box it in a solution for the second part of B. And for C, we're doing the exact same thing, except for this time, instead of N being equal to 350, N is equal to 650. So same equation for calculating the energy and the distance, R. So again, the energy then is just going to be 13.6 electrons divided by 650 squared. So this gives us a value of 3.22 times 10 to the minus 5 electron volts. So the larger N, the less ionization energy required to ionize the electron, which makes sense because larger N means it's farther away from the center of the atom, as we are going to see in the next calculation. Again, R is equal to N squared times Bohr radius, A. So using 50 this time, we find this is equal to 224 times 10 to the minus 5 meters. So it is indeed farther away. We can box that in for our solution for part C.